All right, so we saw that Hamilton paths, Hamilton circuits, how to look for those in certain graphs. And we saw that, the circular graphs have sort of one Hamilton path or the reverse of itself. And we saw that the complete graphs had lots and lots of Hamilton paths that we could look at. So oftentimes, just because a Hamilton path exists, oftentimes we want to do the optimization thing, where we make sure that we spend the least amount of time traveling. So many situations have these Hamilton paths and circuits. And a lot of times in the real world, a lot of things look to be like almost complete, or like complete graphs and their connections. For instance, if I was talking about cities, well, you can take almost any city in the United States, and it's probably, or any major city in the United States, and it's connected by highways, or at least a series of highways, to every other major city. All right? But efficiency is needed in many places. So let me describe what I mean by that. If you have like the United States, right? We have New York City over here. We have Boston over here. And we have like San Francisco in the sort of northern part of California, and Los Angeles in the southern part of California. Now, all of these are connected by highways and by plane. But if you were going to go and travel to all four of these spots, it's a lot more efficient to take from New York to Boston and then to go to San Francisco and LA than it is to take and go from New York to San Francisco and then back to Boston and then back to LA, right? You're going to be traveling a much bigger distance if you crisscross the country a couple of times than you would if you only had to cross one time, right? Now, all of these are connected, but there is a most efficient way to do this, all right? So it's the similar thing can be talked about instead of going from the New York, Boston, San Francisco, LA example. Well, how could you travel from Grand Rapids and Detroit and Columbus and Cleveland and Chicago and St. Louis? All of these are connected by highways. You can get from one to the next. Sometimes it's more efficient to go certain routes. Okay, you probably wouldn't want to go from Grand Rapids to St. Louis and then back to Detroit and then back to Chicago and then to Cleveland and right? There's probably a most efficient way, a best way to travel. Okay, however, in this case, it's not as obvious what path you should take as it was in the New York, Boston, and LA example. Okay, so what we would do on these 6 cities, if we were really doing this, is we'd say, well, let's give each one of these a point. And I'm not going to worry about, at least I'm not going to worry right now, about location. Right? Because location, sometimes it can be deceiving to your eyes. But we do know that these are all connected by highways. So we get a complete graph. I hit a little now. May have them all now. All right. Now, what you would do in reality, and I'm not going to go through this entire example because there's a lot of different paths you can take, but what we do in reality is we say, all right, this edge, let's pretend Grand Rapids is up here. That's a bad color. Let me erase that and get a new color. Let's pretend Grand Rapids is up there, and Detroit is here, Columbus, Cleveland, Chicago, and St. Louis. All right. So what we do is we take each single one of these paths, or excuse me, each one of these edges, and we're going to assign it a weight. And in this case, the weight is going to correspond to how long, or excuse me, how far or how long it takes to go from Grand Rapids to Chicago. And so this blue edge that I've highlighted is going to be assigned a weight. Maybe that's, I don't know, 200 miles, or maybe that's a certain number of hours, 3 hours or something like this. I'm not exactly sure. I don't know the exact number of miles from Grand Rapids to Chicago, but that's the sort of thing you would do. All right? And then you'd have to look at all of the paths and decide which one minimizes the total distance. Now that's why we're not doing it in this case, because if you notice, there's a lot of paths that you could take through this maze. So we're going to do it on smaller scale, but there are computer programs that could check, every single path. So let's pretend your company was located in Grand Rapids. Well, there's computer algorithms that could tell you whether it's better to go to St. Louis and then Chicago and then Columbus and then Cleveland and then Detroit, then Grand Rapids, or if it was better to go, a completely different way through this maze. All right. Now, this is the idea of weighted graphs, where each graph edge is given some certain weight. And usually the problem either has to do with, let's minimize the distance, let's minimize the weight that we have to travel, or there is an alternative problem that says, let's maximize the distance or maximize the weight we have to travel. Okay, maximize what's the worst scenario. And there's different applications for these. The delivery route stuff is obviously generally a minimizing a weight we have to, or excuse me, a distance we have to travel. So each weight is a distance. But there are other types of connections that can be given weight that we want to maximize. All right, so let's do this. Let me take a complete graph on 4 vertices. And I'll give each edge a different weight. Now, just for the sake of time, let's assume we want to start our graph at V1. Or excuse me, our path at V1. Okay. And so let's give our weights to these vertices. Let's take, and I'll write the weights in green just so we can do this. Let's say that's 10, that's 20, that's 15. This one can be 5, this one can be 25, and let's say this one is also 25. So the crosses are 25, and everything else is 5s, 15s, 10s, and 20s. All right. Now there's a couple of strategies that are involved here that you could use. So if we wanted to start at V1, what we could do, we could start at V1. We can employ what's known as a minimizing distance, or excuse me, minimizing the edges strategy. So I don't know how to say that. There's a technical term for that, but basically what you're going to do is you're going to always travel to the next lowest. So if you start at V1, you have a choice between 10, 25, and 5. So if you're trying to minimize, one strategy is always to take the path of least resistance that you haven't traveled already. So in this case, you go V1 to V4. Now take the path of least resistance. 25 to 15 is a 15. Now take the path of least resistance. 25 to 20, go the 20 route. Now take the path of least resistance. 10 versus 25, go the 10 route. All right? So if we took the sort of paths of least resistance method, you go V1 to V4, V4 to V3, V3 to V2. And your total weight you've traveled there would have been, I believe, 50 in this case. Okay. Now here's some hard things when it comes to weighted graphs. One of the first things that, I'm sorry, it would have been not 50 but 40. Excuse me. Yeah, 40. So one of the harder things is to say that there's no other better path that you could have taken. All right? By the way, in this case, V1, V4, V3, V2, there actually is no better path that you could have taken. And if this was I said originally weight was 40 because I was thinking circuits, but if it was a circuit, it would have also traveled on the 10. But anyways, oftentimes it's hard to sort of prove to yourself that this is the best path. Now, again, there's multiple ways of proving that this is the best path. You could say, well, let's travel a different way and see what we get. Or let's travel, this way and see what we get. Lots and lots of options for that. Lots of options to go through. There's another way you could have done it as well and said, well, if I have a path V1 to V2, V1, V4, V3, V2, all right, we know that there is at least 3 edges that we need to cross. Okay? And if I start at V1, right, one of those edges cannot be this one or that one. So if I start at V1, you can kind of convince yourself that that's the way to go because the 25s, these cross-diagonal things, are the highest in the graph, and you want to stay off those. Now, that's not always going to be the case, but you should convince yourself that the total weight of being 40 is the best we can get on a path. On a circuit, total weight of 50 would be the best we could get. All right? So that's the hard part about looking at those kinds of things is this really the best? Now, I do want to mention something because last time we started at V1, if you could have started anywhere and we had this complete graph, well, if you could have started anywhere, you may have had a different result than what would have happened if you were forced to have started at V1. Now, again, in real life, sometimes you are forced to start someplace, and sometimes you aren't forced to start in a place. So you do have to kind of be wary of how that thing worked. So anyways, 25, 25, we had a 5, a 10, a 15, and a 20. Okay. And this one was V1, V2, V3, and V4. So what I was saying is it's pretty clear that if you could have started anywhere, there actually is a better route to go. You can go the 10, the 5, and the 15. So you can go from V2 to V1 to V4 to V3 and have the best path possible. Okay, if you're doing a circuit, then actually those two circuits would be the same, but the one I had on the last slide and this one. But on a path, this is a better path. And this one's kind of easy to prove that this is a better path because not only are we dealing with sort of, these are the closest neighbors each time, but also notice that if you had to travel to 4 different vertices, you have to at least have 3 jumps. You have to at least have traveled 3 edges. So this one's kind of easy to see because we are going with the smallest 3 edges that exist in the graph. All these other edges are bigger. Okay, now it's not going to be that easy every time, but that's what's happening. Now, the complete graph on 4 vertices was, we determined the best method kind of by sort of a mix of the 2 different methods that I was talking about. The brute force method is to test every possibility, every single possibility. The nearest neighbor method is always choosing the smallest distance you want. And we kind of saw how those things work. And in our case, both the brute force and the nearest neighbor led us to the same results. All right, so I want you guys to try on this one. This is a fairly straightforward example. I want you to be able to start anywhere, in this case, and find the best path going that hits all the vertices. Okay. By the way, I want to say, well, I'll say this later, I guess, but find the best path in this case. Push pause on the video and see what you come up with. All right, so hopefully you've gotten that V1 to V4 to V2 to V5 to V3 is the best path, or you could have gone the reverse of that. You could have started at V3 and went backwards along that. So I'm going to start at V3 first. So you could have gone V3 to V5 to V2 to V4 and to V1, and you would have gotten sort of the best travel possible. Now, I do want to say something about these things. What I've been doing is I've been getting Hamilton paths and Hamilton circuits. However, in real life, oftentimes you can retrace your steps. Okay, this one isn't a very good example, but there are times when you can retrace your steps and do some things and make retracing actually efficient for you. Okay, so for instance, if I was going to do a circuit on this, obviously there's no Hamilton circuit where I hit everything once, but if you had to start at V1 and get back to V1, well, you could have taken that smallest path and then just traveled right back on that smallest path. And there might be some other weird thing where you could travel the smallest path and then get, a jump if we had other edges. All right. So just because this doesn't have a Hamilton circuit doesn't mean we can't optimize things. Same thing with other graphs. Just because they don't have a Hamilton path doesn't mean we can't optimize the distance traveled through all the vertices. By the way, the weight that you get there traveling this path, what would that be? 18 plus 6 is 24. 24 for your weight. Okay? So that's the best way to do that. All right, let's take another look and another example. So let me draw that. I'll push pause here and draw it, and it'll pop right up. All right, so hopefully that popped right up for you. Here's what I've done. I've labeled every single edge in this graph, and I want to travel to all 7 vertices, and I want you guys to kind of think through what would be the best place to start, the best route you could take. Now this one is fairly complicated because there's so many different options, okay, and that's obviously done on purpose. All right, so I want you to kind of think through where the best place to start is, and then come up with a good answer. All right, so hopefully you've came up with some ideas, and maybe they might not be perfect, they might not be flawless by any means, but hopefully you kind of get an idea of what we're trying to accomplish here. So what I see is I see a couple of things that, some just overall general ideas, and this isn't meant to be very insightful by any means, but this 100 is the biggest number, 90 is the other biggest number, so you probably want to avoid those ones, okay? Now also, it might not be nice to start at like a V3 or a V6 so that we don't have to travel to V6 and then back to V7, right? If we get in here, we're traveling down here and then travel back and forth, and then we might go. I'm not exactly sure if that would help or hurt or what, okay? It may not. It may not. Again, in this case, by the way, there's no real nice, I don't think there's a real nice Hamilton path that you could take that would get you from one vertex to the other. I think you'll always run into this problem that you would retrace a vertex if we tried it. So anyways, retracing we typically don't want to do. All right. So at this stage, we can employ one of our strategies here. Let's employ let's start at V3 and employ the smallest neighbor strategy. Okay, the nearest neighbor strategy, excuse me. Well, that would mean go to V2 and then to V4 and then to V7. V6 you'd take out right there. You go to V5. You go 70 and then 10. I think we could cut that out by going, instead of going from V5, we could go back that way. That would avoid a 70 and a 10, a 100, and replace it with a 13 and a 20. So this is what I'm seeing as one option. So V3 goes to V2. V2 goes to V4. All right. V4 goes to V7. I'll go to V6, back to V7, back to V5, not back to V5, to V5, back to V7, and then V1. All right. Now, notice that path involved V7 a few times, so obviously it's not Hamilton, but it does give me a pretty good number. All right, or at least it allows me to avoid the 100. It allows me to, well, I had to go from V4 to V7, on the 90, primarily because, once I was at V4, my choice was either to go back 40 plus 70 or to go straight across on the 90. And so what I've gotten here is a fairly large number. And it may not be the best, it may not be, but you're going to have to try a few things out. Okay? And this is just one attempt. I'll let you guys kind of try and see if you can come up, and let me know if you come up with a better weight than what I got. By the way, what I got was I got a weight for this, for the path that I got. The weight was 226. Okay. And notice this one is not very nice. Now, on an exam or something, I'd probably give you something that's a little bit nicer than this one, and it's a little bit less, fewer edges, but I wanted to get you the idea that sometimes this is not nice, this is not pretty. Oftentimes, you're not going to have a nice Hamilton circuit. Sometimes you do, like on the complete graph, you're going to have a nice Hamilton circuit or Hamilton path, but sometimes you don't, and that's just the way things are. Okay, and you have to kind of get used to that and accept and embrace those kinds of things. So I got a weight of 226, and again, let me know if you thought of a better way to do this. If you came up with a weight that gives me less than 226.